Good morning, students. I am Puneet Narayan, Assistant Professor, Department of Electronics and Communication Engineering. In today's lecture, we'll discuss the effect of negative feedback on the input and output resistances of amplifier. Actually, due to negative feedback, input and output resistances becomes modified in such a way that they try to approach their ideal values. For example, voltage amplifier has actually it should have infinite input resistance and zero output resistance. So due to negative feedback, if we apply negative feedback in voltage amplifier, then the effect is the input resistance will increase and the output resistance will decrease. Because why the input resistance will increase? Because it has to approach infinite. It needs to approach infinite, and output resistance will decrease because it needs to approach zero. So this is the advantage. This is the very good advantage of negative feedback. So due to negative feedback, input and output resistances gets modified in such a way that they try to approach their ideal values. Okay. So now, as you know, there are four feedback topologies. Huh? So for each and every topology, we have to derive the expression of input and output resistances with feedback. Okay. Actually, the procedure is same. If we do this derivation for any of one topology, we can easily derive these expressions for the rest of the topologies. So we will take voltage series feedback topology. Okay, please pay attention. Now this is the equivalent circuit model of voltage series feedback topology. This is the input section and this is the output section. Okay, this is the output section. Now for input resistance, what we have to find? We have to find the ratio of Vs, that is source voltage, and the input current. And the input current. Okay, this is the expression of input resistance. Okay, with feedback. Now, how can we find this expression? How can we find this ratio? We have to apply KVL in the input section. Okay, so let us apply KVL in the input section. By applying KVL, the equation comes like Vs equal to II into Ri plus Vf. And what is Vf? We already know Vf is beta V0. Okay. Now to find the ratio of Vs and II, we have to find V0 in terms of some input quantity. Okay. So how can we find V0 in terms of some input quantity? This is your output section. V0 is the quantity of this output section. So we can easily apply voltage divider rule in the output circuit. By applying voltage divider rule, what will be the value of V0? V0 will be RL upon R0 plus RL into A small v Vi. Okay, because AV is the voltage in the output circuit and there are two resistances connected in series, R0 and RL. So what will be the value of voltage across RL, which is basically V naught? V naught will be RL upon R naught plus RL into AV VI. Okay. So now at this point, let us assume this quantity AVVI, AV RL upon R naught plus RL equal to A capital V. Okay, there is some reason behind this. We will discuss it uh, in a few moments. But if we assume this, then what will be our equation will become? V naught will become A capital V into Vi. Okay, this is our equation number 3. Now let us discuss A small v and A capital V. Okay, what is A small v? A small v is basically, we already know, in our previous lectures we have already discussed. What is A small v? A small v is basically open circuit voltage gain without feedback. Okay, now what is A capital V then? A capital V is basically voltage gain taking load into consideration. Okay, it is also without feedback. Okay, now if we need to find the relationship between A capital V and A small v, previously we already assumed this quantity, we already know the relationship. But if we need to find another one important relationship, we can also write A small v equal to A capital V when RL tends to infinite. Means if we open the load, A capital V will become A small v. Okay, this is basically the relationship between A small v and A capital V. Okay, now from equation 3, V naught equal to A capital V into Vi. Vi we already know. Vi is basically II into Ri. So we can put the value of Vi in this equation. Now V naught will become A capital V into II into Ri. Now this is our equation number 4. Now put the value of V naught from equation 4 in equation 2. If we put this value of V naught from equation 4 into equation number 2, the value of Vs comes equal to II into Ri plus beta A capital V into II into Ri. Now from this we can easily find the ratio of Vs and II, which is basically our RIF, input resistance with feedback. So what is the value of input resistance with feedback? Input resistance with feedback comes equal to Ri into 1 plus A capital V beta. Now we can easily observe that input resistance with feedback is very much greater than Ri. Means due to negative feedback, our input resistance increases. Okay, now we will derive the expression of output resistance. Look, there is a procedure to find the output resistance in any circuit. There is a certain procedure. You have to follow that procedure only to find the output resistance. Now what is that procedure? To find the output resistance, you have to open the load you have to apply. No, before applying, you have to open the load and you have to replace all the independent sources by their internal resistances. You have to follow these two steps before finding the output resistance. This is the universal procedure to find the output resistance in any circuit. Okay, you have to uh, open the load. Secondly, you have to replace the independent sources by their internal resistances. Now, step third, you have to apply an external voltage or current source, and you have to find the produced voltage or current by that voltage or current source, and you have to find the ratio of these two quantities. Now we can apply voltage source or current source. In this circuit we can find output resistance easily by applying the voltage source. Now we need to apply a external voltage source having value V. So a voltage source is applied. Now we have to find the current I produced by this voltage source. If we are able to find this current I, then by finding the ratio of V and I, we can easily find the value of output resistance. Okay, so how can we find the value of I? Just apply KVL in the output circuit. By applying KVL in the output circuit, I will become what? V minus a small v Vi upon R naught. Okay, this is our equation number 1. Now from KVL in the input circuit, Vf now Vf is now become minus Vi. Okay, so Vi is minus Vf. We can put the value of Vf also. Vf is what was the value of Vf? Vf was beta V naught. Okay, what is the value of V naught now? V naught is voltage across the output terminals. What is the voltage across the output terminals now? It is V, which is our external voltage source. Okay, so Vf now becomes beta V. So what will be the value of Vi? Vi will be minus beta V. This is our equation number 2. Now putting the value of Vi in equation number 1, I will become V plus a small v beta V upon R naught. Now from this equation we can easily find the ratio of V and I, which is V upon I is equal to ROF is equal to R naught upon 1 plus a small v beta. Now you can easily observe by this equation that output resistance without feedback is R naught and output resistance with feedback is ROF. So output resistance with feedback is now reduced, means output resistance is reduced now due to negative feedback, because ROF is equal to R naught upon 1 plus AV beta. 1 plus AV beta is having value larger than 1. Okay, so our previous conclusion, now we have proved our previous conclusion that input resistance and output resistance. In case of voltage amplifier, input resistance will increase and output resistance will decrease. Okay, but it is not universal for each and every topology. Input and output resistance gets modified in such a way that they approach their ideal values. Some amplifier have input resistance, ideal value of input resistance 0, and output resistance infinite. So in that case, input resistance will reduce and output resistance will increase. This is the advantage of negative feedback. Okay, now we have to find out one more quantity, which is basically ROF dash, means output resistance with feedback including load. How can we find this? How can we find this? Let's go to our next slide. Now look, for understanding this, we have to go back to our main circuit, main equivalent circuit model of voltage amplifier with feedback. This is our main equivalent circuit model of voltage amplifier. The topology is voltage series feedback topology. Now this is the uh, output circuit. This is the output circuit. Okay, so what is ROF? What is ROF? ROF is, wait a moment, ROF is this. This is ROF. And what is R naught? R naught is this. What is the relationship between ROF and R naught? You can easily look into the circuit and conclude that ROF is basically parallel combination of R naught and RL. Okay. No, 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 no. Wait a moment. ROF we already find. We need to find ROF dash. Sorry, sorry, sorry. Wait a moment. ROF dash. ROF dash is basically ROF including load. What is a load? RL. So ROF dash is basically output resistance seen looking into the output terminals. So what will be the value of ROF dash? ROF dash will be R naught parallel with RL. Okay, it is simple. So let's go back to our derivation. This is our derivation. So ROF dash is basically parallel combination of ROF and RL. Okay, so this is the derivation of ROF dash. We have to do some simple manipulation. Okay, this is the simple manipulation, and after that we will find this expression. This is our standard expression of ROF dash. What is ROF dash? ROF dash is RO dash upon 1 plus beta A capital V. What is RO dash? RO dash is parallel combination of R naught and RL. Okay, and what is A capital V? A capital V is A small v into RL upon R naught plus RL. Okay, so now we have derived all the three quantities. First of all, we have derived RIF, and after that we have derived ROF, and after that we have derived ROF dash. These three derivations, these three expressions we have to find for each and every topology of the feedback amplifier. Uh, the procedure is same for each and every topology. We have discussed in detail for one topology. We can easily repeat, we can easily use this procedure for other topologies also. So thanks for now. We will meet in our next lecture with some new topic.